Okay, I think we can start. Welcome all to the second lecture of the Missing Semester 2026. The topic for today's lectures is the command line environment. And yesterday we covered the cell and we saw many programs that you probably didn't even know that were in your computer and that you could launch them and actually combine them through the cell. You know, there was like a lot of information. I feel like unlike a lot of other concepts in programming, the cell has its own quirks. It also has like historical concepts. And today in the lecture, we're going to cover a lot of the kind of concepts that are like specific to the cell environment and that you should get familiar with so that when you're going through these programs, you understand exactly what is going on. And then in the second part of the lecture, we're going to see how to operate more efficiently kind of in remote machines and also how to like change the behavior of your command line and your environment. And as always, like if anything is unclear, feel free to ask questions during the lecture. So the first thing we're going to cover today is like, if you've seen any other type of programming, the kind of the inputs and the outputs of programs are usually very clear, right? You have like in a function like this in Python, you have like your X and Y arguments, and then you have your output, which is another value. And that makes it fairly easy to understand. But then as you start writing or reading other people's shell scripts, it can become quite confusing exactly what are the inputs and what are the outputs of this type of scripts. So for example, here we see that we're getting some value in some way, and if that doesn't exist, we're exiting. We're accessing maybe variables that are not defined within this script. And just to be clear, you should not understand what's happening here, but this script has like pretty much examples of all the concepts that we're going to cover today. And there are like multiple types of input and multiple types of output in shell scripts. And there are conventions that pretty much all programs follow because you're communicating between programs that maybe were written by very different people. So the most simple type of input that we already saw yesterday is the notion of arguments. So when we run the command ls and then we give it like -l project1, we're giving it input in the form of arguments. And here arguments are nothing special, just like strings. And when we run this, we're telling ls, and ls is getting both -l and it's getting project1 and is parsing them in order to decide what to do. And actually, most programming languages will have like a way to get this information. In Python, this is the syntax. And so you can see there's nothing special going on. We can just run Python with exactly the same inputs. And we can see that when the cell calls or program with these inputs, we're just getting literally the name of the input program and then the arguments. And it's up to the program how to interpret these arguments. Here we find the first convention that is pretty common in the cell, which is the notion of flags. Flags are like when you have an argument and it has this like single dash or double dash, and that tells to the program that this is an option, that it should kind of change its default behavior. And when you go into the manual page, you will often see many of these flags documented. To be fair, like the cell doesn't require that you actually use this like dash or double dash syntax. It's just like everyone kind of agreed upon this, but you will find programs that don't do it. So further, like the convention usually is that when you have a single dash, is usually like a single letter that follows. So for example, -a means to also list the kind of hidden files, which are like by convention as well, the ones that start with dot. So if we touch like a file called .a and we try to ls, that file is not there, but when we do -a, it suddenly appears. And that flag is equivalent to doing -- all. Kind of it's the same. It's just like you can think of -a as a shorthand to call the same option. You can have multiple flags in different formats when you call programs. Usually the order doesn't matter. You can give them in any order. And a lot of the time with these single character flags, they can be combined. So when I do this, it's identical to all the commands that I've run previously. One important thing to note here is the cell is not giving us these features. All these features of like parsing the flags to allow you to do the syntax is because the ls program is actually doing parsing to allow you to do this. And that's why when you write cell programs, you will most often use libraries that automate a lot of this parsing for you. And there are conventions, so like it's really common for like -a to mean all. It's pretty common to have -h be help. So like you can most often rely on programs having like help or like version as their options. And I feel like that covers most things about flags. The other arguments that you usually get with programs are just strings. And when, for example, when we do this program, project 1 is just like a string passed to ls, and then ls determines that it interprets that to be a file. Another common convention when you're working in the cell is for programs to accept the same type of argument an arbitrary amount of times. So for example, when we do mkdir, we can use it to create multiple folders, and we can, for example, create project 3 and we can create project 4, but instead of calling it individually, what we could have done is we could have just done this. And many programs will will accept an arbitrary number of arguments, and they will do the same operation in each one of them. It is not guaranteed, it will depend on the specific program, but the reason why you want to do this is, even though for this example it not might be that convenient, in a case where you want to say, for example, delete or like touch, for example, touch is a command that just updates the modification time. If you want to update all the Python files in this folder, we can do touch *.py, which is a type of pattern matching that is called globbing. We already saw some examples yesterday. But the important thing here is when we do this, the touch program is not getting *py as its inputs. The *.py is getting expanded to try to match all the files in this folder that have this pattern. And in fact, if we go back to our kind of very basic Python script that just repeated what was received, we can verify that that's the case. When we call it with *py, we're seeing that all of this is actually what the script is receiving. Globbing is kind of a very simple language. It's not nearly as powerful as, say, regular expressions, but makes a lot of really common patterns fairly simple to do. So, for example, if we want to create like a few files in this folder, you can probably guess by the syntax used here what's going to happen. And what the cell is going to do is expand this by doing like the common pattern that is in here. And now this makes it really easy for us to specify more complex patterns and operations. So we could also update all the, say, like Python files and shell scripts that we have in this folder, and this will get expanded to every single file that matches this pattern. In some programming, in some cells, like for yesterday we were seeing the born again cell. Here I'm using the C cell, which is like a different one. It supports more complex globbing. So for example, we can list, for example, all the Python files, and this will like this double asterisk with match nested folders. So we can see like we are getting like even, and we're navigating the whole structure. And again, this is useful because there is this convention that many programs will accept multiple arguments. Then the next concept that we're going to cover is the notion of streams. So yesterday we were seeing that when we launch programs, we were giving them inputs and they were producing outputs. So when we do something like something like this, so we have this file with just a bunch of numbers, and then when we concatenate all these programs, we can, wait, why is it not? Oh, I think it has to be quoted. So for example, in this case, we have like this rect which says only filter like single numbers with a single digit. And one thing that I want to emphasize here is when we say like inputs are getting connected to outputs, that's because when we execute a pipeline in the cell, it's not like we're running the first command and then we're running the second command and then we're running, no. Like we're actually running all these programs in parallel, and we're connecting the outputs of programs to the inputs of the following one, and then as output is produced, is already consumed by the next process in there. So we have this Python script, which is a really simple script. It will just produce numbers slowly from 0 to 10. And if we were to run this and pipe it into grep, so we can just check for all the kind of odd numbers. We have to, it's Python by default buffers, but we can see that as numbers are getting produced, they already, like, both programs are running in parallel. And as the first one is producing output, the second one is kind of consuming it and producing its own output. And you can get fairly kind of complex things, or like when you launch like a pipeline like this, here the first command is actually like we'll see later what happens when we use the ampersand command. But when we do this, we're just launching this pipeline. We're putting an ampersand at the end to put it in the background. So, because it's going to take a while. But when we do this, if we check what processes are running in this machine, you can see that sleep is there, grep is there, sort is there, unique is there. Cat is not there, and that's because cat will not start until sleep completes. And once, like now, everything has complete, and we get the output. Now, the programs will have like a standard input, which is how they get their information.
Can you reorder what the computer is doing in terms of it's processing all these different things, right? Can you change the order of which job it's doing? Like say, no, I actually want cat to happen now before he does something else. Does it sense like
yeah, right here, what's happening is, I mean, cat is not running until sleep complete because we put this ampersand. Like the double ampersand is the kind of an operator. Like cat will only execute if this program executes successfully. But in this case, yeah, like we could just remove the sleep, and then cat will like happen immediately. And then the pipes are just the flow, like they define the flow of information. Then most programs expect like input through the standard input. So for example, grep, usually that's how it grabs the information. Grep can also get it from a file. So for example, when we do this, just giving it a file. It is convention that when you just do a single dash, that means the standard input. So if you ever see, like, this is not like in this case, this dash is not a flag. It's just like, it's convention for this to represent that you want to read from your input. If we have an input, but we actually have two outputs. When kind of a program produces its output, it can produce it to what we call the standard output stream or the standard error stream. So when we do ls, for example, and we kind of list, this is by default going to the standard output, and we can send this to, actually let's delete the file first, but like we can send that information to files.txt, and then files.txt has now the value of whatever output this program produced. However, if we try to ls a folder that doesn't exist, now we get this kind of error message. And if we try to capture that error message, we haven't captured it. And that's because that didn't go to the standard output of the program, that went to the standard error. In order to capture the error, we actually have to use different syntax. But this is convenient because now programs have a way to communicate both of these types of information without them getting mixed into their output. One common pattern that you might see is sometimes you want to ignore the output, and that's why you use this dev null. So there's this notion, there are some special files, dev null, for example, whatever you write to it, it just disappears. It actually doesn't get written anywhere. The next concept that you'll very commonly see in the cell is the notion of environment variables. When to define a variable in Bash, you use the syntax of foo equals var. And to access it, we use the kind of $foo syntax. It is quite important to know that foo equals var with spaces is not valid. Right? When we try to do this, what we're actually telling to the program is run the program foo with arguments equals and argument var. And then it tells us, program foo doesn't exist. So we have not defined this variable. We can put many things in variables. For example, we can capture the output of programs into variables. And because there is conventions that usually programs will look at inputs by splitting by new lines. If we echo this command, we see everything split by new lines. And then if we try to run grep on top of this, we'll see that grep is operating line by line, even though we put everything into a variable. Now, some variables are kind of special in that they whenever you create a variable, it goes into kind of your current local session. But sometimes you want those variables to be passed into other programs that you define. So here, we created foo equals var, but if we try to create a debug equals 1, and then we run this program, which is just saying spawn a cell and check the value of debug, it's not there. And that's because by default, when we did this, it was only set for kind of the local cell. If we actually want to pass that, we can call it directly. We can prepend the command with that. And now when this program gets launched in its environment, it will have this variable. The reason why environment variables are useful is because there are some conventions on some variables that are commonly used. For example, if a program wants to save configuration, it might check the home environment variable. So whenever you're running a program, your operating system is setting this home environment variable that says the home folder for this user is here. So instead of having to run my command and always specifying whatever is my home folder, the programs can almost often assume that this environment variable is defined and use that for their operation. Another example is yesterday we saw the date command that just tells us what date it is right now. But for example, if we use the TZ environment variable and we say, actually, we're now in Asia, Tokyo, and we run date, we'll see that the output that we get is different because the date command, it's checking for this environment variable and changing its behavior based on that. And that it's useful because, for example, time zone is something many programs need to know, and it would be really annoying if you always had to do date and then specify the time zone manually.
So the local variables you create only persist for that line.
For the cell session. So like if I do debug equals 1 and then I do like ls or whatever, and I do like now debug again, it's still 1. It will be set, but child processes will not inherit it unless I do export. Like if I do export debug equals 1, I'm telling, okay, now all the children process that I create should also get this variable. And now if we go back to this example, before we were getting nothing here, but now because we exported the variable, it will get it.
What does bash.c do?
Bash.c says, okay, run a bash cell running whatever I have on the right. Just like a way of running like if I do echo debug, it will just execute exactly in my session. This is a way of creating like a child cell. The next concept is like we've seen that we can we get inputs through environment variables, arguments, and the standard input. We produce output through the standard output, but there's another output that we also produce, which is the return code. Like usually the standard output is just like a bunch of strings you can think of. But in many cases it's useful to signal whether the command that we ran was successful or not. So the idea here is when we run ls and everything went well, we can actually check, okay, what is the return code? And the return code is just another string that is a number, and in this case is 0. And the convention is 0 means everything went well, non-0 is there was an error.
If I run export debug equals 1, and then I run debug equals 2, what value will the child shell have?
It will have, when you prepend, that has, so the question is what happens if you export and then you use the prefix?
If I use the export and then I run debug equals 2 on its own.
Oh, debug.
And then I run the child shell.
I see. In that case, I think it should be 1. Because I export.
Like, I'm asking, like, does export, like, make it a shared scope, or is it, like, does it just set the value that will be copied?
Yeah, the idea of export is you want to export it to all the child processes that this cell will create.
But is it like the variable itself is getting?
So like if we delete debug, right, and we try to access it in the child process, it's not there. If we just set it here and we try to access it in the child process, it's not there. When we run export and we try to access it in the child process, it is accessed. It's like the value is set.
The question is perhaps if you now modify debug, is the modified debug also modified in the subshell?
Yeah.
Yeah, I think so, because you already have declared that it's exported, right? Yeah.
Okay, yeah. Thank you.
Yeah, sorry, I was not understanding the question. So going back to what we're covering, so when we run ls, if it goes well, we have this notion of return code. It worked. If we try to ls something that doesn't exist, and we check the return code, it's actually 2. It's like something went wrong. What went wrong? This was not like a folder we could actually list. Most of the operators in the cell language will rely on return code. So for example, what we saw yesterday of using like ifs and whiles, like almost any control flow, they will not look at the output of the program. They will look at whatever like return code they produce. And in many cases, it can be fairly useful because, for example, grep will produce like 0 if it finds the pattern, and it produces like non-0 if the pattern is not found. So we can use the grep minus q. So So if we use the ampersand, which is kind of like the AND operator, the second program will only run if the first one runs successfully. And the opposite version of that is if we run the pipe, which is OR, the second command will only run if the previous one fails. I think that that covers most of like return code logic. Yeah. Oh, minus q is by default grep. If we just run it, will output whatever it's doing. The minus q is equivalent to saying quiet. Like run, try to match, but don't give any output. And the reason why quiet is helpful is because we might be using the return code of grep. The last kind of cell-specific concept is the notion of signals. So again, yesterday we saw this idea that you can have like a command that is running for a while, and then you can do Control-C and it suddenly stops. But like what is happening behind the scenes for you to send this Control-C and then kind of the program actually knowing that it has to stop? So this is happening because we're sending what are called signals. Signals are a type of software interrupts, and what's happening is the cell is sending like a signal to the program with a specific code, and the program is receiving it, and if it has a way to deal with it, it will run that code. Otherwise, it will probably just exit. So when we do this, what's happening is we're sending the second signal, and we can actually write programs that do different behaviors based on this. So for example, this is a Python program, and Python has the signal library, and we can define a handler that says like, okay, I got a second, but I'm actually not going to stop. And when we do this, we're just saying, okay, whenever we get a second, we're gonna execute this function, and then by default, this is just going to count numbers. So if we run this command, we see that we're counting numbers, we try to Control-C, and it's not stopping because we have a way to process what's happening, and we are deciding to ignore it. There are many more signals. For example, if we do Control backslash, we're sending SigQuit, which is like a more aggressive, like, you should really exit. And there are even more aggressive ones that can't be handled, like SigKill. Their documentation online, like there are many, many different options that are defined, but actually in practice you only be using a few of them. One of the reasons why this might be helpful is, say, for example, you have a script that uses some temporary files, and you want to guarantee that even if something goes wrong and someone interrupts you, you actually clean up those files so they are not like lingering. This is what we're doing here. This is the same idea of we have a bash function that says like, okay, let's clean up the temporary files, and in case we get like a SIGINT or like a SIGTERM, then actually call this function. And in here, we're just creating the file, sleeping, and then deleting it. So if we run this command, and then we Control-C, we see that we actually run that piece of code that handled the signal. There are signals that don't just interrupt the programs. Another common one is Control-Z. So when we send Control-Z, what the cell does is sends like a seek t-stop signal that says like, okay, the terminal told you to stop. So the program gets suspended. It gets kind of like paused. And now if we check kind of what processes we have, we can see that there is this process that was suspended. We can kind of recover it. We can kind of like send it back. We can also send signals to that process using the kill command. You might maybe have seen kill. Kill is just like a way of sending any type of signal, not just one to stop the program. So for example, here we can send the continuation signal to this suspended process, and this is the process ID, which is how the OS identifies it. And if we now check, now we see it went from suspended to running. But if we wanted to still interrupt it, I think actually it's left, but like, yeah, we can, like now we have another process that is suspended, and we can interrupt, or like we can continue. And then we, instead of doing Control C, which we can't because it's suspended, we can just interrupt it. And like we interrupted it by sending the signal explicitly through kill. Okay. And I think this covers a lot of the abstractions. You will kind of, there are a lot of conventions that you've seen of like having flags, reading from standard input, taking arguments, having arguments that are like, all of them, like taking many, like an arbitrary number of arguments and operating in all of them. And as you use more of the cell on your everyday, you will find that a lot of this just makes easier to use new programs because a lot of them are just abiding by the same rules. The next topic we're going, yeah.
When you kill a process though, if it's generating data or files, what happens to what is cache generated? Does it clear its cache or like what happens?
Depends on depends what the process is doing. Like for example, in the one that one script we wrote, they had some intermediate files, but because the program had a way to dealing with the interruption, it had a way to clean things up. By default, it won't. By default, like if you just write a program and don't consider that possibility, you actually might have like half-written files. The next topic we're going to cover is the idea of working in cells that are not in your own computer, but actually running in a remote server. For this, we use the secure cell, which is SSH, and syntax can look something like this. We are calling SSH and saying we want to authenticate as user JJGO, and this is an IP address. IP address is like kind of the more low-level way. You might have seen something that looks more like this. In practice, that kind of server.mit.edu, it's looking online at someone to tell it that it's actually this number. Oh, and I have to delete this. So usually when you SSH, it will prompt you for the password. You need to show that you're like authorized to access this server. So we type the password and we are now in this machine and we can ls, we can create files, we can do pretty much the same thing. One of the annoying things is whenever you exit, you don't want to keep kind of like re-authenticating. So for that, we rely on SSH keys. SSH keys use a thing called public key cryptography, which is like a private key and a public key. And with that, you can kind of show that you're authorized without having like to type your password. In order to generate key, you will run a command like this. Here's asking me to override. And now we have produced two files in the file system. You can kind of ls SSH, and we can see we have a private key and a public key. This public key is, public key is a piece of information that you can give people so that they can verify that you are who you say you are. So if we put this in the remote server, then they can verify that we actually own the private key. When you, for example, want to upload code to GitHub, for GitHub to know like that you are who you are, you're probably going to give them kind of like your public key and they will use that to verify. The private key, in contrast, you should never give to anyone. This will not leave your computer. This is equivalent to your password. You should never copy paste this. It's fine for me to put it because this is just like a temporary key I'm creating for the class. Like just never paste your private keys anywhere. So in order for the server to know about our private key, we just run this command. It will ask us for the password. And now whenever we try to SSH again, we didn't have to type our password because it actually used this SSH key to verify that we were actually authorized here. And if we check the SSH authorized key, that kind of magical SSH copy ID command, the only thing that it did is just copy that one string that allows the server to verify that we have the private key. Then SSH is useful for interactive sessions, but you can also use SSH to execute commands. So if we do that, it will just execute ls, but it will execute ls in the remote machine, and then it will, whatever output it produces, it gets forwarded to the output of SSH. Like SSH is not a magical command, it's equivalent to almost every command, so it can take input and it can produce output. So for example, if we do this, where wc.l just counts lines, what's happening is we're running this through SSH, we're getting the output of whatever ls produced in the remote server, and then we're counting the lines locally, like the wc is running in the local computer, not in the remote one. If we wanted both of them to run in the remote computer, we will do that, and then now the entire pipeline executes there. One challenge when dealing with remote machines is sometimes it can be challenging having like many things running in parallel, because you have to like SSH and now you have like a cell, and say that I actually wanted to, actually we should first cover copying files. So if you want to actually copy files from your local folder to your remote machine, there are many programs, but almost all of them are just using SSH under the hood, which is good because you already configured your SSH key. So for example, if we want to copy the ignore.py file, and then we say, okay, it will be copied to this server under this path. This is like this specific syntax that SCP takes, and we need to go to demo. And it just says, okay, yeah, I successfully copied this file there. And then now when we go there, we can see that ignore.py is here. Issue is the moment we try to run ignore.py, actually I have 3 here, we cannot do anything else in this remote machine. And this is where terminal multiplexers, where the most famous one is tmux, come into play. Terminal multiplexers are just programs that make easy to run many other programs within the same environment. So when we run tmux, you'll see that now we have kind of the same prompt, but now we have this bar here. This is running in the remote machine, and we can, for example, run our process, and giving it the right keystrokes, we can create more panes for us to keep working. So like, for example, we can kind of start editing the file while the process is running in a different one. We can create more windows. So windows here is just the nomenclature that tmux uses, but it just, you can think of it as browser tabs. So for example, here we can see that there's like 0 and there's 1, and then we can switch between them. The nodes have like a lot of the keyboard shortcuts that tmux uses. tmux uses type of keyboard shortcuts that is not that common, which is prefix-based keyboard shortcuts, where you usually always run Ctrl-B, then release that, and then you type some other key. So for example, in order to create a new window, you do Ctrl-B, and then you do C, and that tells that we want to create a window. If we do Ctrl-B 0, it tells us to go to window number 0. And there are many things that you can do. Like for example, we can now leave all of this session running. So we can do Ctrl-B D for detach, and we can reattach again. One of the advantages of this is if we just had this program running and we disconnected from the remote server, we will have lost it. And because when you actually disconnect from a remote session, what the cell does is it detects that and it sends a special type of signal called the hang-up signal. So it's like sig-up, and that will kill all the processes that were running. Tmux decides to capture that signal and actually doesn't propagate it. So now, if we connect to the server again and we do tmux.touch, we can see that everything is still running. And this is quite convenient because now our kind of remote session is not tied to the connection between the two servers.
So when you make the SSH keys, like you can also do passphrase?
That's a great question. You should definitely do it because. Oh yeah, sorry. The question is, when you create an SSH key, should you add a passphrase? And I'm saying that's a good question. You should definitely do it. If you don't, what you're effectively doing is you're putting in your file system the password to effectively SSH into these servers. Any program that has the ability to read your file system will probably be able to read that file as if you don't add a passphrase. When you add a passphrase, you're effectively kind of encrypting it with your password, and whenever you want to SSH into a server, you will get prompted to decode the key. And then I think the notes have some examples. There are programs that actually make that a bit more convenient. But yeah, you should put passphrases in your SSH keys. The next topic that we're going to cover is actually customizing your cell. So by default, your cell will come with many programs that are installed in your operating system. But for instance, maybe when you try to repeat whatever we're doing here and you run Tmux is not available. And that's because in some distributions, Tmux doesn't come pre-installed. And in order for that program to be available, you have to install it. So for that, the kind of unfortunate news is different operating systems have different ways of installing programs. So if you're on Mac OS, the kind of de facto package manager is brew, and Debian and Ubuntu is apt. And if we wanted to ensure that Tmux installed, we will do something like this. And as you try to run kind of more and more programs, you will find that a lot of the time you have to figure out a way of installing them. The programs there are like many programs out there that actually make interacting with the cell easier. So for example, there's like grep. That is like a kind of more versatile version of grep, just makes your life easier. And we can try saying, okay, I want to find all the Python files that have import in them, but it's not installed. And what the cell is telling us to do is like, okay, you should install grep. And once we do that process, now that program that wasn't available before is now available. And we can actually search for all the files that have import in them. It might not be obvious why, if we were trying to do RG, we had to do grep, or like why grep is like RG, like that mismatch can sometimes be frustrating. There is this fantastic website that is called Command Not Found. You type the program that you don't know how to install, and it pretty much tells you in a bunch of different operating systems how to install it. Your first instinct should always try to go to your package manager. The next thing that we're going to cover is just modifying how your cell behaves. So yesterday we saw that there's this kind of path environment variable, right? And that the path environment variable has this list of folders that contain all the programs in your operating system. Now, with what we've seen about the different properties of the cell, we know that the way to modify the path so it has more entries that it has is just doing variable assignment. You can say, okay, path is whatever it was before plus this new path that we're trying to append. And we probably want to set export because otherwise any child processes will not inherit this.
Is our current location the thing at the end of the path?
Is our current location? No. The path is a variable that has like if we echo path, right? It's a variable that has the contents, that had exactly this content. And then if we make a folder and then we move into that folder, the path variable hasn't changed. It's the same. Does that make sense? Like by default, the cell will not try to use your current folder to find programs. And that's why yesterday we saw that if you create a script, you had to prepend with like // to tell it that to actually search in the current path. If we try to do a script.sh, it will tell us this is not a command I can find in any of these folders. But if we run the export, right? And now the value of path is different. It has that extra entry that it didn't have before. And we could search, it will search in that path. The challenge is now if we disconnect and like we reconnect and we have like a new session, if we echo path now, we have lost that modification. That modification, even though we exported it for child processes, it's not getting persisted. Like new sessions do not know about that export. The way to actually persist that configuration is to add it to the cell configuration file. That will depend exactly on which cell you're running. In the remote server, we're running bash. So if we look at the bash configuration file, which is bashrc or bash profile, depending on the cell you're running. Here is pretty basic, but the main idea is if we include the export path in here, now whenever a cell process is created, it's going to read this file, it's going to evaluate this line, and then path will have this entry. So we can verify this by disconnecting. We can connect again, and then if we echo path, we can verify that it has that extra entry that otherwise it wouldn't have. And their path is a special variable. There are variables that modify other parts of the behavior of your cell. So for example, here we have PS1. PS1 tells the cell how to render that left prompt. So right now it's getting rendered in this way, but if we overrode that saying PS1 is just like this plain symbol, if we now spawn a new cell, you see that now it's just that symbol, there's nothing else. And in order to have that nice behavior, we have to use a specific syntax that the cell understands. When you're kind of trying to find commands, you might try to use the history. So for example, I know at some point I've run a vim command. I can search like I can do like a backward search through my history to find like different things I've vimmed. But the cell also allows you to override that behavior. So in this case, what we can do is we can load another tool, which in this case is FZF, which is a fuzzy finder. And this tool will hook into the cell and will override the control R behavior. So, well, actually we can, like the way to do it without exiting is doing source, which means evaluate line by line that file. And now if we try to control R, we get that we get like a fuzzy finder with all the bashrc, all the vim commands that we have run. And there are many, many things that you can customize about your cell. And there are like entire plugin systems of things that you can do. In practice, a lot of people will document online how their setup is configured, and that's usually called dot files. That's because most of these files would start with a dot to make them hidden. So it's like dot bashrc, dot /shrc, and people will have many of them kind of committed for just them. It's for them to keep track of, but it can actually be really useful to read through them and understand what they're doing. So, for example, in this case, we can see that this user didn't want globbing to take whether like a letter was uppercase or lowercase into account. And there is this command that you can use to tell the cell not to pay attention to be case insensitive. And there are many, many options that you can give, and people have documented a lot of them online. One extra detail is, in order for you not to lose your configuration when you go to a different machine, it actually pays off to put it into a single place and then install that into your current environment. To elaborate on that, if we now do ls-la of this folder, actually let's grab bash, we can see that my basrc file is actually not a file. This is how ls illustrates having symlinks. Symlinks are a notion in many operating systems, which is, this is kind of whenever anyone tries to read this file, just go somewhere else, like read this other file instead. So this is saying like, okay, whenever you want to read .basrc, you should actually go into dot files basrc. And this lets me put all my dot files under like dot files, version them, I have them on GitHub, and then whenever I want to configure another computer to have all the options that I'm used to, I just have a script that actually creates all these symbolic links so that the programs can find the configuration files. And yeah, like the dot files for all the 3 structures of the course are online, and you can check them, try to like understand. I recommend not blindly copy pasting like an entire basrc from someone without understanding what it's doing, because it might get really confusing. What the defaults they chose is actually more useful, kind of going line by line and understanding. Yeah, so there's actually a very useful link in the lecture notes that elaborates on why there are multiple files and which ones are read when. So Bash has different files depending on whether the terminal was interactive or not, and that's why you have like basrc and bash profile. So for example, if it's an interactive session like the one we're seeing here, basrc will be read. When you actually launch bash not interactively, then it will not load that part of the configuration. For csh, it's like a different cell, and it has a different file. So like you can configure the 2 of them completely independently because they are going to check completely different files. So like if we check for here, we have to go up one level. Like there are like csh for like chrc, they're like different files that are related to csh. The next notion is the notion that there are many things that you can configure, and there are things that are not built into the cell but can be convenient. And people build entire packages to support some features. So, for instance, you probably have seen that throughout, like in this terminal, whenever I type things, it tries to give me a way to autocomplete based on previous commands I've run in the past. This is not the default behavior. This is because I told csh to load like a bunch of files that enable this behavior. And the lecture notes have links to plugins that do these things, and they can make your experience more convenient. So for example, here as well, kind of when I type ls, it's getting highlighted in green, and that's no coincidence. It's because the ls command actually exists. If I do ls X, it's red because that command doesn't exist. And I don't even need to run the command to see that it's not going to work because it's not available. And if I type the name of, it's demo. Oh, well, that was like a good example. When we did demo, because demo was a folder that existed, then that immediately got highlighted. And it's not worth covering every single of these plugins, but you should be aware that they exist and that they can make your terminal experience way more convenient than the stock configuration can do. And we have links on a few of these plugins. Some of them will also configure how your prompt look like. So for example, here it's telling me that I'm this user in this machine, and if I go into the .files folder, it's going to tell me things that are only relevant in this folder, such as in this Git repo, we're in the master branch, and there are like 5 changes that we haven't run. Or for example, if we try to ls like a non-existent thing, the cursor changed to red because the return code of the previous command was non-zero. So like a very quick way for me to get information that I probably could get as well by doing it manually, but it's just much lower effort.
Do those plugins work on the WSL version?
Yep.
And will it work in no matter which directory you're in, or whether you go to another shell or also to things? Works whenever you're on your machine, or you have to specify?
Okay, so the question is A, whether this will work in WSL. The answer is yes, because WSL, for the most part, you can just think is like a Linux machine running your computer. And then the other is about this will affect all cells, or like all folders. I feel like folders, yes, because as you navigate, you're still using the same cell session. Like you're using the same program that is running in your computer with this configuration. But if you're, for example, using CSH that has some configuration, and then you start like a bash session, that will have a different configuration. Actually, I think I can, like if I run bash, you can see that the prompt is different because the configuration that I have for bash is different from the one I have for CSH.
And did it tell it to load in these plugins?
Yeah, like the CSH cell is reading completely different files in order to set up things like the plugin system that I described that enables that things, and bash in this case, I actually haven't modified because I like it as a fallback if anything breaks, and it's just using pretty basic configuration.
And how do you tell it to load in these plugins?
So if we go to the CSHRC, there will be, there's actually, for example, there's this like power level 10K prompt plugin that it's the one that is actually coloring like kind of like the left prompt and the right prompt. And what this line is doing is saying, okay, if this file exists, right, which is the condition in bash, and then we're using the operator that we saw earlier that will only run if the previous one succeeds. Wait, what? Oh, it's using, okay, there's negating. I don't know why I did that. That's just weird that they do it that way, yeah. But like, if this doesn't exist, this will fail, and then this is run, and then source is this command that will just evaluate line by line whatever this file contains, and then this file that we can actually just look as well. It's an entire plugin done in CSH that enables a lot of these behaviors.
Basically, a giant bash program is the plugin.
And how do we get that bash plugin? Do we just copy it from somewhere and put it on the machine?
So
I'm kind of slow.
In that particular case, a lot of these plugins will live in GitHub, and there will be an installation section that it tells you exactly how to install it. Here, the most simple setup is you literally git clone, which is download that repository of files to your local machine under this specific path, which is like your home folder, and then add this line that enables this to run.
You write that line in a bash.
Yeah, look, what this is doing is you will write this line in your CSHRC, but if you look at what's happening here, it's saying append that to your CSHRC. So you don't actually have to do it with Vim. You can literally just run this, and it will append that to your CSHRC.
Thanks.
Oh, and one very quick note, you might see entire frameworks that load many, many plugins. I feel like the kind of most known framework is OmyZSH. Those frameworks can be good, but they can also slow down your cell because they're trying to do a lot of things for you. They're like enabling a lot of behaviors. So I actually recommend just installing one plugin at a time, seeing if you actually use it and it's actually worth for you. And if not, you just remove it. I feel like having that fine-grained control prevents bloating your cell experience. And as a last topic, I want to quickly touch on how we can actually use AI tools in the cell. So you can always go to ChatGPT on the website and ask it questions about the cell, and they will definitely work. But you can actually interact with these models using CLI tools, and that might be more useful and more convenient. So one tool that you can install is this LLM tool. It's linked in the lecture notes, and here we're pretty much saying okay, I want a command that just finds all the Python files that were modified in the last day. I know there is some syntax with the find program that will achieve this, but as we were seeing with John yesterday, sometimes it's hard to get all the right flags for find. And this will ask an LLM that will have a really hard time not to give us the right answer, and it just prompts us that whether we're fine running this command, and we can quickly inspect it, and it makes roughly logical sense. Its name is *py, the things have to be files, and they have to be modified in the last day. And if we run it, they're kind of all listed. Beyond that, we can also use LLMs as part of our processes. So, for example, here we have a file where we have many different usernames in widely different formats, and I'm sure there exists a regex to extract them here, but it's just much simpler to define a variable that is, okay, just give me the username for each line and nothing else, right? And then we can give that to the LLM. And again, this is a good example of the LLM program is getting the instructions through an argument, but the kind of input through the pipe, and then we output it, and then we give it to sort. And as you can see here, it's extracting the relevant piece of information for every one of the lines that otherwise that unstructured parsing could have been quite challenging. The last tool that I want to cover, it's Cloud Code. So Cloud Code, it goes step beyond that, where you can give it instructions in English, and it will translate a lot of them into all cell operations or operations in your file system. So you can think of it as a meta cell program, except the programming language is English. So actually don't remember what the So we can give it instructions, something okay, use find again to get the most recently modified cell script, and then change the shebang line to use zsh. Something probably you could do, but again, find has a tricky syntax. And what the LLM is doing here is taking all instructions, is producing this bash command, which probably looks extremely alien and full of unclear things, but if you unpack it, it actually looks fine. It's just searching for .sh files that are executable, and it's trying to extract which one was most recently modified, runs that, and instead of us getting that output and having to figure out how to feed that output into the next command, it's actually determined that it was actually cleanup.sh, that was the most recently modified file, and is proposing that we change the shebang line to go from bash to zsh. And it can be a really powerful tool when you actually don't know do you need to know some of the intermediate specifics, or avoiding having to kind of take the output of one of the commands only to figure out how to fit it to the next input. And then we can accept it. The very last thing to cover is, so far we've defined like the cell, and we have been like running it through like some program. In this case, will depend on the operating system. Here we're using what it's called like a terminal emulator. It's like a GUI program that it's running the cell and just presenting it in our computer. And there are different options. And again, as with dot files, you should look into which terminal emulator you can run. The one I'm using here is Alacrity, and it's like a similar thing where there are options that you can configure. For example, today, for this lecture, what I had to do was change the font size from 16 to 32. And if I write that, it goes back to the size that I usually have. So it's, again, worth it to kind of, when you're trying to improve and customize your cell environment, don't forget about what terminal emulator you're using. And I feel that concludes the lecture for today. If anyone has any question, happy to answer them. Also happy to like answer questions individually.
Thanks.
Thank you.